Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, Mastering AI Inference Infrastructure to Maximize ROI, brought to you by Tech Online, Achronix, and broadcast by AspenCore. I'm Colleen Heckman, and I'll be your moderator today. I have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on today's slide deck in the resource box located to the right of the presentation window. At this time, we recommend you disable your pop-up blockers. You can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area located to the right of the presentation window and then click the submit button. If you're experiencing any technical problems during the webinar, please type your issue into the same Q&A text area, hit the submit button, and we'll be glad to offer one-on-one assistance. And now on to the presentation, Mastering AI Inference Infrastructure to Maximize ROI. Discussing today's topic are Jansher Ashraf, Director of Business Development at Achronix. Jansher is a technology leader with 15 plus years of experience in the technology sector, focusing on full stack AI ML industry from SaaS to AI ML infrastructure. At Achronix Semiconductor, he drives strategy for AI ML inference solutions, helping enterprises deploy large language models and speech to text with lower latency and lower TCO compared to alternative solutions. And joining Janser today is Raymond Nyssen, Vice President and CTO at Achronix. Raymond has over 25 years of experience in the FPGA and EDA industries in various senior technical and management positions, covering hardware, software, systems and application engineering, as well as hardware and software architecture. He drives Achronix technology innovations, which he has resulted an industry first, giving Achronix differentiated technology leadership in the FPGA industry, such as the machine learning processor and 2D NOC. It's with great pleasure I now hand things over to Janser to begin. Janser, take it away.
Thank you, Colleen, and thank you to everyone else that has joined us today. We've been looking forward to this for quite some time, so I'm very excited to be here as we go through our presentation. And if any questions come up, I'm certainly looking forward to discussing those, so please keep those coming. So I will review the roadmap for our session today, where we'll begin with an overview of AI inference. Then we'll look at the current AI inference landscape, how it's evolving, and what are some of the notable trends that we're seeing. And from there, we'll dig into AI's value add, specifically why conversational AI is reshaping industries. And next, my colleague Raymond will go over strategies to maximize inference ROI, and that will include model optimizations to hardware efficiency. And then we'll talk a little bit about how Achronix delivers on those principles. And then I will show you a demo and a preview of our solution as well. And then finally, we'll have our Q&A session that I'm looking forward to. So let's start by understanding why inference is so crucial. So one can argue that AI at the inference stage is where the action really happens, meaning that's when AI becomes real. AWS and Harvard Business Review recently released an article, for example, which stated that little over a third of large US enterprises have AI centers of excellence. These centers of excellence focus on people and process to enable the adoption of AI. This shows that AI is a core business driver, and more importantly, it places an emphasis on AI adoption by the workforce at large, especially from a leadership point of view. But with all this adoption comes a new challenge. Inference becomes the dominant cost driver. And that's because once a model is trained, it's inference that powers the day-to-day interactions. Every Q&A interaction, every transcription or translation, or even meeting summaries customers see, that's inference in action. The one way to think about it would be training AI models gets lots of headlines, but takes a few weeks or months. But inference runs every second of every day. That means most of the AI spend and energy consumption happens during inference. So the largest cost driver becomes the inference infrastructure. and therefore the need to optimize inference infrastructure for scalability, low latency, and most importantly, cost efficiency becomes crucial. And this is where the industry by and large is focused on. So as we zoom out and take a look at the broader AI inference landscape and try to understand what's actually happening in the market right now, what's clear is that the inference landscape is changing quite fast. Majority of the AI activity today, either in the cloud or on premise or with edge deployments, they revolve around inference workloads. Across the industry, we're seeing some trends. So CapEx for all major hyperscalers is still growing, and they're also diversifying hardware vendors. There was an article just recently released by Goldman Sachs where it was stated that US hyperscalers CapEx are expected to triple to $1.4 trillion by 2027. That's just in a couple of years from now. And AI clouds or neo clouds, they're focusing more on the software stacks and becoming vertically integrated to differentiate themselves. And then there's the open source ecosystem of models. And that system is still thriving and in turn is increasing price pressures on closed source model API providers. And then the AI PaaS providers that are optimizing for cost efficiency while using hyperscaler infrastructures, they've attracted notable funding from the VC ecosystem this year as well. And the hardware itself, that's certainly going through a refresh cycle, and all of it really is aimed at efficient inference and supporting lower precision number formats, for example. And at this point, inference is becoming its own discipline. It has its own benchmarks, cost models, and an ecosystem. But one thing is clear that the overarching objective of the entire industry is to improve token economics when it comes to the inference stage. So now let's take a look at one of the most visible examples of this with one of AI's biggest value adds. So when we talk about AI value, conversational AI is front and center of that. Because let's take a look at the evolution of human machine interfaces and how they've changed over the last few decades. In the 80s, for example, we had the graphical user interfaces or GUIs, and then the browsers in the 90s and smartphones in the 2000s. Today, we're in the era of conversational AI with LLMs. And LLMs make interactions intuitive and human-like. Whether it's a chatbot, a voice agent, an AI assistant like a meeting summarizer, for example, it's the most intuitive interface yet, meaning we can finally interact with the technology the way we interact with each other. In fact, according to the Wall Street Journal, 75% of contact centers are expected to use generative AI within the next few years. This shift isn't necessarily just about convenience. It's about efficiency and engagement because there are real world impacts, meaning conversational AI is transforming industries, it's transforming support, content creation, and even emotional well being with AI companions. But scaling all of these experiences brings a new set of challenges, like sustaining inference performance at those scales. Now, when addressing the challenges of scaling AI inference efficiently, that's where things start to get interesting. And also, they start to get very expensive because each interaction, each query, each response, it generates an inference request. And enterprises are handling millions of these on a daily basis. So here we can connect the dots, where on the left you see typical AI use cases, chatbots, copilots, translation use case, or voice agents. Each of these depend on four key inference requirements: low latency, high throughput, scalability, and of course, cost efficiency. And on the right, we can see what that delivers to the business itself, because it's better customer experiences, which are typically measured with customer satisfaction or CSAT scores or net promoter scores, lower cost, faster ROIs, and also compliance readiness. All of this really just captures the essence of why inference optimization isn't just a technical issue, but it is a business imperative. So how can inference ROI be maximized? Well, for that, I will hand it over to my colleague Raymond to discuss methods to do just that. Raymond, over to you.
Thanks, Jancher. In this section of the webinar, we'll look at the main objectives, requirements, and methods to maximize ROI of AI inferencing tasks. ROI maximization is, of course, the main make or break business criterion that drives which hardware and software solution will get selected to perform these workloads. The universe of AI inferencing workloads has already gotten wide and diverse, with no single solution that will deliver the best ROI across this universe. A solution with compellingly high ROI in one scenario may have unacceptable or even negative ROI in other scenarios. The focus here is on what matters most in large data center scale production deployment scenarios of conversational AI workloads. This space is characterized by relatively short input and output content amounts, tight demands on response times and generation output flow, and a focus on application domain specific expertise. TCO is the main ROI optimization objective that we focus on here. We express CapEx in terms of dollars per token of content. This is the cost to install the infrastructure that is capable of processing a specified volume of content per time unit. For example, if you want to operate a data center that can generate 1 megatoken of content per second continuously, how much does it cost to build a data center that can handle this workload? OpEx is dominated by the amount of energy needed to process a specific volume of content. For example, what will be the energy cost when that data center processes and generates this amount of content? TCO optimization is subject to quality and performance requirements. Quality of results is a measure of the value of the generated content using a given model. Importantly, quality is a function of the application domain, as we will see in the next slides. QR is measured by means of standard public benchmarks with scoring functions. This enables QR comparisons between solutions. QoS, or quality of service, is to track the response time performance of a solution. Different application domains will have different requirements. These requirements are primarily expressed in terms of ITL, or inter-token latency, or TPS, and TTFT, the time to first token. For example, verbal interactive conversations with an AI system require fast initial response times, followed by relatively slow content generation rates in order to match spoken word flow. In contrast, written prompt response applications allow for a longer wait time until the first responses are generated, which is then followed by a much faster output content generation rate for reading. QoS is measured by means of standard performance benchmarks like GenAI-Perf. These benchmarks provide a way to validate that given QoS requirements are satisfied by a conversational AI solution, and they enable comparisons between competitive solutions. Subject to these requirements, in the next few slides, we'll review the following ROI optimization methods. First, right sizing of the models, then optimization of those models, and then deployment on the most cost-efficient infrastructure. The main takeaway here is that the deployed solution for conversational AI must be highly conducive to these methods in order to maximize ROI. Model specialization is an effective method to optimize ROI of a conversational AI solution. Here we look at the size of an AI model in terms of the number of weight parameters in the first place, but also in terms of the model complexity from a computational effort point of view. Large and very large size foundational models are great at generating high QR across all round knowledge domains. However, this comes at the expense of QoS and TCO. This is because it requires more computational effort to generate output from a larger or more complex model. So it takes longer to produce the initial output, and the rate at which content is output will be slower. Likewise, from a compute resource usage and power consumption point of view, the output is more costly to generate than smaller models. In many applications, there is no need for an all-round solution. Therefore, model developers take foundational models and reduce them in size to focus on domain-specific knowledge. Within the focus domain, QR of the specialized model will be on par with the all-round model used within the same domain. Therefore, within a given domain, such smaller models deliver better ROI than the big models. The extent of reduction will vary depending on the desired trade-off between QoS, QR, and TCO. Each such model is specialized toward different domains and to varying extents. This leads to a large variety of models that a versatile AI inferencing solution must be able to support. This multitude of models will continue to grow rapidly over time, driven by TCO and QoS optimization forces. A related development is called mixture of expert models. These successfully demonstrate a way to deploy models with a large number of parameters that need to be stored, while computational effort is reduced compared to a traditional model. MOE models have been shown to generate output with QR comparable to all-round models of similar size with better TCO and QoS. This trend will also continue to lead to a rapidly and ever-increasing diversity of the model zoo. These and other approaches, current or future, also adds to the requirements on the underlying hardware. The main takeaway here is that a high degree of flexibility is required from the AI inferencing solution so that model reduction developments can indeed be leveraged to maximize ROI. On the previous slide, we looked at optimization of model size in terms of the number of weight parameters. On this slide, we look at additional related concepts of model reduction. The main technique we'll talk about here is quantization of model weights. Quantization of weight values is a procedure that converts numbers expressed in a fine-grained representation into a coarse-grained representation, meaning that it can express fewer different values. These quantized values take up less space in memory, so you can store larger models with the same amount of memory resources. Likewise, you can fit the same model using fewer memory resources. ROI improves from either point of view. The process of quantization is well researched. Here, I'll just say a few things about how this relates to better hardware compute efficiency. The quantization process is not as straightforward as simply rounding the original values to a smaller set of discrete values. Doing just that would result in an unacceptable loss in QR due to excessive clipping and quantization noise that you would introduce that way. To overcome this, a concept called group quantization is used. This refers to techniques in which the model's weight parameters are partitioned into groups that share a common scale factor. This results in effectively negligible rounding errors. What matters here is the following. In order to fully leverage this technique, the underlying hardware must natively support it. This is best done by means of so-called block floating point arithmetic. Standardization of these formats was done by the OCP Alliance through the microscaling formats standard, which has been getting broader adoption in recent years. An example is the MX int8 format. Operations carried out in this format are much more area and power efficient, while the results are equivalent to those using floating point arithmetic. In summary, here I focused on quantization as a key example to emphasize the importance of high degrees of flexibility of an AI inferencing solution in order to best translate such optimizations into actual ROI gains. Next, I'll cover what key hardware architectural features and capabilities are required to deliver best ROI when performing these very compute and memory-intensive AI inferencing workloads. First and foremost, the hardware must provide a balanced mix of these features and capabilities and those must match the inherent characteristics of the application domain. To that end, first, you need high bandwidth, high capacity memory. This is imperative for inherently memory bandwidth limited workloads like LLM inferencing in particular. They are used to store model weight sets, and all weights need to be reloaded very many times in order to generate model output. Next are right-sized flexible compute engines. You need adequate compute performance to satisfy QoS requirements, and these must support flexible number formats for future-proofing and efficiency. In order to maximally utilize all the hardware resources, you need high bandwidth on-chip data transport, and it must be able to saturate all data streams from memory, compute engines, and all data interfaces. And it must be able to deliver all this bandwidth ubiquitously and uniformly across all hardware resources. Finally, you need high bandwidth data interfaces. These are needed in order to scale out the workload across multiple parallel accelerators in a system in order to optimize QoS. And last but not least, you need performant host processor connect. The extent to which a hardware platform can provide competitive ROI will be seriously diminished if it does not provide all of these resources, features, and capabilities to the required extent. For example, imagine a hardware platform with many compute resources providing very high compute performance, but with memory bandwidth that can keep those resources utilized for only a fraction of the time. QoS of that platform is then held back due to the lacking memory bandwidth, although cost and power usage of that hardware is higher due to those extra but unusable resources. In other words, the overall solution will only be as good as the weakest link. Next, we'll present how Achronix FPGAs help customers optimize ROI of hardware solutions for low-latency LLM inferencing workloads. I will now speak to why FPGAs that satisfy the requirements that I covered in the previous slides deliver superior TCO, especially with low-latency applications. As we've seen, conversational AI imposes low-latency QoS demands. Such low latencies can only be satisfied with low batch sizes during LLM inferencing. Batching is a technique in which model weights that are loaded from memory get reused across multiple tasks in the same batch for computation. When multiple tasks can be batched together as one, that changes the ratio between loading operations and compute operations proportionally to the batch size. LLM inferencing at low batch sizes is inherently memory bandwidth limited. This means you'll then have underutilized compute resources waiting for memory. This is commonly referred to as the memory wall. A hardware platform with excess compute performance has the major disadvantage of being unable to utilize these expensive resources, which drives up cost per token and energy per token. The roofline diagram depicts this relationship between memory bandwidth and compute performance. In the low latency area, the cost of these excess compute resources drives up TCO for no QoS or QR gain. FPGAs that satisfy the requirements that I covered in previous slides have a far smaller cost and power burden, as they provide matched compute performance and memory bandwidth. Let's now look at a prevailing drive in the industry that has been dominating and will continue to dominate the drive toward greater performance and greater cost and power efficiency of these AI inferencing solutions. Namely, the number formats used to represent model weight parameters and the precision of the arithmetic operations used to compute the mathematical functions of the model. These are primarily linear algebra functions, namely large matrix multiplications of activation data with model weights in particular. Initial developments in this space started with standard floating point representations, such as FP32. These were soon found to have excessive numerical precision, which is very costly in terms of processing resources, power, and wasted performance. Since then, relentless efforts to quantize these models down to ones with fewer bits have led to the current state of the art using 8-bit floating point formats. These use a fraction of the memory resources required to store the model weights and a fraction of the processing resources. In terms of hardware cost and power to perform the numerical math, reduction of bit widths of number formats has a quadratic benefit on cost and power. The green curve in the graph shows roughly in what year a number format with a certain bit width got adopted. The labels are the names of the number formats, and the number of bits is on the green y-axis. It is worth mentioning that recent novel number formats are essentially block floating point formats where a block of elements share a common exponent. The orange curve represents the amount of compute power that can be accommodated by the same amount of hardware resources. This is not even accounting for semiconductor scaling. Note that this curve is on a logarithmic scale. For the last half decade, the number of bits of these operations has been reduced at a rate of about 2x every 4 years. As shown by the graph, the efficiency benefit of this reduction scales roughly quadratically with this trend. Crucially, these TCO and QoS benefits have been achieved without compromising QoR. Given the huge benefits of further number format scaling, industry and academia continue to drive this trend further. Breakthroughs with implementation based on ternary and even binary formats have already validated this direction. Additional techniques are likely to drive this trend even further. In order to translate these recent and near future developments into actual TCO gains, you need hardware platforms that guarantee a very high degree of flexibility, offering fine-grained bit-level granularity of programmability. The rapid developments on this front also require such high degree of flexibility in order to future-proof an infrastructure for AI inferencing workloads. This is so that such ROI optimization developments can be deployed most expediently using the same hardware investments. Given that FPGAs provide these capabilities, these trends strongly favor such FPGAs. However, this is provided that the FPGA product also satisfies all the requirement capabilities that I mentioned in the previous slide, namely with respect to very high compute capabilities, very high memory bandwidth and capacity, on-die bandwidth transport, and finally, high bandwidth scale-out and host connect features. With this, I'm handing the presentation back to Genscher, who will cover how Achronix can help you optimize ROI with the current and future conversational AI deployments.
Thank you, Raymond. So at Achronix, we deliver inference efficiency through three optimized solutions. First, we have our hardware solutions comprising of our FPGA, which has thousands of MLPs or machine learning processors, which are compute engines, and high bandwidth GDDR6 memory, and a 2D network on chip for efficient data movement. We've embedded this into an accelerator card we call VectorPath 815, which is a double-wide PCIe form factor card. Second, we integrate with standard data center ready appliances. These appliances house the VectorPath 815 card, and we work with off-the-shelf servers for a quicker time to value and easy scalability. And third, we have our optimized AI models. These are pre-configured models optimized for our hardware solutions addressing AI inference workloads that require low latency, high throughput, and most importantly, cost efficiency. Pre-configured models really means that we've completed all the steps required to run leading models on our hardware solutions. So we've done the quantization, the memory management, the compute utilization, everything required to run performant and cost-efficient inference for either ASR workloads or LLM workloads, or combining the two for conversational AI workloads. Our pre-configured ASR models have been evaluated by third parties and offer less than a 3% word error rate. One VectorPath card can process up to 2,000 real-time streams simultaneously. Our model garden of pre-configured LLMs includes the Llama family of models and other open source models. And the LLMs configured on our hardware solutions have been evaluated for quality of results or QOR benchmarks and have no quality degradation, especially when compared with unquantized versions of these models. This means the models perform exactly as expected. Now let's take a look at a sample turnkey appliance for inference workloads. So this is one of our AI inference appliances. This is using an off-the-shelf server equipped with 8 vector path cards. Each of the cards are powered by our FPGAs. It's really a drop-in solution into data centers, meaning with this setup, you can scale horizontally by adding more cards or nodes as your inference demands grow. So whether you're serving ASR models for transcriptions or LLMs for text generation or other generative AI use cases, or combining the two for conversational AI, this appliance is designed for low latency, high throughput, and cost-efficient inference at scale. This is also the appliance that's actually housing the cards and the optimized models that you will see in a demo shortly. So our solutions are really the foundation for an ROI scenario that I'll go over on the next slide. So here's a real world scenario of what the economics look like. With the workload requirements of generating 1 million tokens per second running continuously for 5 years, the TCO with the Achronix solutions is just $4 million inclusive of the CapEx and the OpEx for that 5-year period. But the revenue generated at today's prices for, let's say, an 8 billion parameter LLM is about $35 million. That's a little over $30 million of gross profit, or in other words, nearly a 9x ROI. This ROI really comes from the cost per token and not just raw performance. So I invite you to contact myself, Raymond, or Colleen to get in touch with us for a TCO or ROI analysis of your workloads and see how our solutions can address your inference demands. So today we've talked about conversational AI use cases, including ASR, LLMs, and the need to optimize these models and for them to run on efficient infrastructure. So now I will show you all of this coming together in a short demonstration. Okay, great. Thank you. Yeah, so I will show a demo of our solutions. On my screen, I'm logged into the Achronix AI console, which is a front-end web application designed to showcase AI models running on our VectorPath 815 accelerator cards. The models I'm using today are optimized to run on our accelerator cards by one of our partners, Myrtle.ai. They're based out of the UK. The cards and the appliances themselves, however, are hosted here in our own managed colo in North America. So for this demonstration, I already have a sample transcription of a conversation between a contact center agent and a caller, which I'll paste from my clipboard here. Now, once the transcription is generated, it's an excellent input into LLMs deployed within conversational AI applications, especially for downstream tasks like summarization or sentiment analysis. Now, as I click Summarize on the right-hand side here, this will use the Llama 8B model, which is a smaller model, but it's excellent at summarization tasks. And I'll click Summarize, and we can see the summary appear quite rapidly. It talks about what the caller has, what the caller has chosen, and we can see the performance metrics of this particular summary or this particular request, where the entire summary was generated in under 2 seconds and just about a quarter of a second for our time to first token. Now, for larger enterprises that are processing millions of minutes of transcription or tokens for LLMs, that's really where we add value with our solutions and provide substantial TCO advantages, and in many cases, 10x TCO advantages relative to alternative solutions. So now I will also click the sentiment analysis, and we can just see the sentiment of this transcription, which is positive. And to conduct this sentiment analysis, it took less than 1 second. Now, while I've been showcasing the summarization and sentiment analysis use cases, in the background, I've also been transcribing my speech using a speech-to-text model that is configured to run on our vector path cards, as you can now see. This is real-time transcription, we can see, and we can conduct a summarization or sentiment analysis on this as well. So I'll click Summarize, and we can see the summary of this transcription. And as it would be of no surprise, the summary includes everything I've just talked about for the last couple of minutes. And we can see the performance metrics for this summarization request as well, where this summary was generated in under 2 seconds. So that concludes the demonstration. So thank you for watching. I will now hand the proverbial microphone to Colleen. Thank you.